Okay, after that introduction, thank you for inviting me to speak here. And I hope that this session proves helpful to some of you, or all of you at least, or to all of you somewhat, and to some a lot. So I'd like a little information about the audience here in terms of who has, first of all, who has ever used propensity analysis as a statistician, okay? And who has heard of it or seen an article where it was used, didn't understand it maybe? Okay.
Our colleagues in Kirksville are raising their hand.
Okay.
Hi, Jane.
Okay. What was the hand for hearing about it or for using it? Okay.
Using.
Okay.
We got two here.
Thank you very much. Okay, so I will, the way I've written this talk up, it will be probably for people who know a little bit about statistics. There's only a little bit that requires you know a lot about statistics. And maybe I should ask one more question before I start. Who has heard of logistic regression? Okay, and who has used logistic regression? Great, that's a great start because that's key. Okay. So in this talk, I will talk about why we're talking about propensity analysis. Basically, when we have observational studies, that is, studies that don't have randomization to treatment groups or exposure groups, we do not have the same sense of causation that we get when we do a trial. There's always going to be some degree of selection bias, so we want to try to minimize that in our analysis. So we'll talk about covariate imbalance. We'll talk about how propensity scores can be calculated and how they're used. That's quite a bit of the talk. And then I have two examples to show you how it's been used in a literature or in another study. And finally, just some limitations and a summary. So this is an article that we'll talk about at the end, which was an observational study looking at early coronary angiography for people with non-ST elevation myocardial infarction, which is a subtype of heart attack if you don't know what that means. And when they looked at those who received angiography of the coronaries early, they seemed to have lesser mortality than those who had more conservative treatment where they would wait and not do early angiography. They might do it later. And those two percentages are significantly different with a very significant p-value. However, there was selection bias as in all studies that aren't randomized, and so they later on did some propensity analysis to look at the data. So if we have, in any study we have confounding covariates that we want to do something about, we have three typical methods for dealing with this. One would be matching. So match on those covariates, the two groups, stratifying, and covariate adjustment. I'll talk a little bit about each of those. So when you do matching, you'll realize if you've done it before that sometimes you don't have enough, let's say you have two groups, treatment, control, or exposed, not exposed. You won't have enough good matches. It'll turn out there's an imbalance such that you can't match each case to a control or each treatment person to a control. So you run out of good matches. Stratification, when you make subclasses, you can see in this example that if you had even a few covariates, maybe 6, each of which only was binary and had 2 categories, you would end up with 64 subclasses of data. And it just grows very quickly where it gets unwieldy and the subclasses may have very few members in them. And finally, covariate adjustment using regression is used all the time. However, you might run into the case of overfitting, which basically is you take, in logistic regression where you're predicting an outcome, yes, no, you take the smallest group of the yes, no's, and you are allowed, in general, various people say, somewhere between 10 and 20 cases in that smallest group per covariate or per variable you're going to use in regression. So if you have a study with, say, 30 outcomes out of 100, and or 30 people in the treatment group and 70 in the control group, and you want to predict something, well, you're going to end up only being able to use a couple of predictors, because 10 to 20 per group, and you only have 30 in the smallest group. So that's called overfitting, when you see people write articles where they have adjustments for 7 variables and they have very small n. And those articles, if they make it to the literature, weren't reviewed very well by the reviewers. So what is propensity? Well, I've given you a bunch of synonyms for propensity. You can take any one you like to see what best fits what propensity analysis is. But basically, it's propensity for of 2 groups that are being looked at, say a treatment group and a control group. What variables predict membership in that group, that is treatment and control? We're not looking at the outcome, we're looking at the actual groups that you're seeing, if there's a difference between them in the outcome. So we're going to look at the propensity to be in one of those groups based on a method which we call propensity score. So we take all the covariates that might have some relationship to being a member of the treatment group and the control group. We do usually logistic regression, and we come up with a number. So if you remember, logistic regression will give you, for every member of a set, a number between 0 and 1. And so that will be the propensity score in this example, where, again, we're predicting membership in the treatment group. So we take all the data, we look at things that correlate with membership in the treatment group. Then we do logistic regression and come up with a score, which is a tendency for that person to have been assigned to the treatment group. We don't care at this point if he or she was assigned to it or did get the treatment or not. We only want to know what the tendency was based on our model, which predicts membership in the treatment group. So we look at the covariates that are related to the membership in the treatment versus control group, and we get a score, which is the propensity to receive treatment A, which we'll call the real treatment. Treatment B may be the control, or the even placebo treatment. Then we take this score and we get one number, again, between 0 and 1. And we get it usually by doing logistic regression, which I mentioned, where we put in the regression model all the variables or covariates that relate to membership, yes or no, in the treatment group. We do not look at the outcome variable at this time. That would be not addressing the idea of selection bias, which we're addressing by looking at what predicts membership in treatment and control group. At the end, we'll get involved with the outcome. So we only look at covariates related to the treatment group assignment. So we run logistic regression and we get a score, and it's the predicted probability, again, between 0 and 1. It's the probability that that person would be assigned or would have gotten the treatment, whether or not he actually got it. It's probability from 0 to 1. And I'll mention a bit later, you can actually take that probability and do a logit, or the log of the odds given that probability. That P over 1 minus P is the odds of the proportion P. If any of you have seen that before. The odds is always probability over 1 minus probability. And log of odds is used a lot in logistic regression and some other applications. But you can either use the P you get, or you can transform it to the logit, or log odds. Now, what'll happen is you'll have, let's say that B is the people who received treatment and A is the people who didn't. And when we do our regression, we'll look at the propensity scores, and we'll see in general, it has to make sense this way, that the people who actually got the treatment were more likely to get it based on predicting that with our model. So the scores for being in the treatment group will be higher, and they'll be lower in the group that didn't get the treatment. However, almost always there'll be some reasonable overlap of scores. And we can see that there's an overlap. However, at those dashed lines, we see that there are only control group with scores less than that value on the left, and only people who got the treatment have scores above the value to the right of the dashed line. But all in between, there's varying numbers of each group who had those same propensity scores. Again, the propensity is the chances of being assigned to the treatment group, but regardless of whether you actually were in it. Because if you look at that, you will see that if you go to this dashed line, I don't know if this will work here, probably not. The dashed line on the right at the bottom, we see that scores for A coming down. Well, right near that tail, we have people who have a pretty high score, suggesting they would be assigned to the treatment group. However, we see they're not. They're in the A group, the control group. We also see at that other dashed line, the end of the B distribution, there's people down there that have pretty low scores, yet they actually got the treatment. So there's all kinds of overlap, and there's all kinds of values for both groups. So what can we actually do about this? Well, it turns out that basically those patients with a very similar or the same propensity score, let's say anywhere from 0.4 to 0.6, somewhere in the middle, in a sense, based on our prediction, they were equally likely to have been assigned to get the treatment or not, because they had the same propensity score to have been assigned to treatment. However, some of them actually got the treatment and some didn't. And although I don't know who could prove that these people in this group were randomly allocated to get that treatment, some people, or most people that write about propensity analysis say it's as if people with similar scores, some of whom got A and some got B, it's almost as if they're randomly allocated because they have similar tendency to have been assigned, but some were and some weren't. And so they say it's almost like randomizing them now to be in group A or B. So for example, propensity score of 0.6, let's say we have some people with treatment A and some with treatment B, but they had the same tendency to have been assigned to treatment A, yet some are in A and some are in B. And so most of the experts will say those people are very similar to one another. They have similar propensity scores. Therefore, we can use that to make our analysis better in several ways. So are there any questions so far? Do you get the idea that if people with similar propensity scores are similar to each other, regardless of whether they actually get the treatment or not? A question? Yes, that's the idea that those people who have similar propensity scores, whose scores overlap regardless of what group they're in, they are similar to one another. It'll turn out though that we, depending on the method of using propensity score, we may use all the people in the data set, or we may just use those who overlap. Yeah, another question. You look at by screening, for example, you can do chi-square tests, you can do t-tests, you can do just simple correlation, see which things are related to getting the treatment or not. Those are covariates that are related to being treated. Then you put them into logistic regression and some will pop out, but you get a score again between 0 and 1, predicted probability at the end of logistic regression. So good. Okay, so if the propensity scores are balanced across two treatment groups in a certain range, then we say that all the covariates that made up that score are balanced, and therefore that's why we're saying perhaps they're almost randomized to be treated or not because they have similar propensity scores. And so we can use it as a way to measure the comparability of the treatment group versus the rest. Okay, so now how are we going to compare treatments adjusting for propensity score? Because we can do, let's say we just have an outcome yes, no, and we have treatment yes, no. We haven't done any propensity analysis. We can do a simple logistic regression and predict who gets the outcome yes, no, and we'll get an odds ratio. And it'll be the odds ratio of being treated more or less likely to result in the outcome. But that's totally unbalanced and there's no adjustment for anything. So when we use propensity scores, we can use the actual score. We can use, as I mentioned, the logit or the log odds of that proportion or that number between 0 and 1. Or we can do something even more, can't be more different, but it's different from the others. And it's something that I hadn't used before called inverse probability treatment weighting. And I want to try to explain this to you because I thought it was just a different kind of thing I've never, had never run across before. So IPTW, inverse probability of treatment weighting, takes the inverse of the probability score to weight the observations in the treatment group. So take a number, take a probability 0.01 is the propensity score. The inverse of that would be 1 over that, or 100. And I'll show you in a graph, a table, how that looks. You do that a little bit differently though for the control group. So let me show you that before we go on. So to do inverse probability of treatment weighting, we look at the treated group, we take their propensity score and we invert it and we get a number. So 0.01 turns into 100. Let's take a member of the control group with the same propensity score. Both of these people were predicted to not get treatment, right? Very low probability of being assigned to the treatment group from 0 to 1. But however, one of them was treated, one of them wasn't. If we take, instead of the inverse, we take the inverse of 1 minus the probability. So that 0.01 turns into 1 divided by 1 minus 0.01 or 0.99, and we get about 1. Okay, now let's take another example of control group that had a very high probability of being assigned to treatment, yet wasn't. And we do that inverse weighting and we get 100. So what does this all mean? How would we look at this? Normally when we say people have similar propensity scores, we would say this treated patient and this control patient had this very same propensity scores, 0.01. So we could use them in a way that I'll describe in a minute called matching. However, with the IPTW method, we would look at the inverted score and we would match the treated person with a 0.01 to the control with a 0.99 because they both have scores of 100. Now, what does that mean? How are we analyzing the inverted scores? Well, think about it. In the treatment group, if you have a 0.01, you're not expected to get treatment, yet you did. So that's very interesting. Why was that? Because you weren't expected to. In the control group with a 0.01, you weren't expected to get treatment and you didn't. So that's not that surprising. However, if you're a control with a high propensity score, the inverse weighting gives you a high number, which now if you look at it, the treated with a propensity score of 0.01 is similar to the control of a propensity score of 0.99 because they both have an inverted score of 100. In other words, you want to say, of those who got treated, how surprising was it? Let's take those who were surprisingly treated, which would be that first row. In the control group, let's look at those who were surprisingly untreated, as opposed to they were expected to be treated based on their score. It's sort of a flip way of looking at propensity. In the first case, the typical case, again, we're looking at similar chances of being treated. Here, with the inverse score, we're looking at similar unexpected or expected treatment. So here we're comparing unexpected treatment to unexpected control. Because that treatment person with a PS of 0.01 is not predicted to be treated. The control with a high propensity score is predicted to be treated, yet isn't. So we're taking sort of like unusual cases and matching them together, which is the inverse method. Question? Well, we don't know anything about treatment yet. We're only saying get the treatment or not. Yeah, we're saying, yeah, right. But we're trying to make this assignment to treatment and control more balanced in some way, instead of just saying it's unbalanced and we can't do anything about it. So again, this is a very different way from what I've previously done. So in the treated group, the inverse weights more highly those who were unlikely to receive treatment, but did. And in the control group, it weights more highly those who were likely to receive treatment, but didn't. And they say that makes a more informative balance of matching. Again, we're not matching on or getting people with similar scores who got treated and didn't, which is what normal propensity is. We're flipping it around and we're saying, let's look at those who have unusual assignments and see how they compare, instead of those who get the predicted assignment because they weren't likely to get it in the first place, or they were likely. It's a very unusual way, and I think an interesting way, but as we'll see, depending on which analysis you do, you can get different results, and then who's to say which ones are the right. And one article that I saw mentioned that as you get extreme values of propensity score, so kind of down near the bottom or top, those scores may have an extreme influence on results, and I don't have time to go through the whole explanation of that, but just realize that usually at the tails of distributions, you get funny behaviors anyway. Okay, so how can we then take the propensity score and use it to analyze our data now that we're finally to the point of doing an analysis? And just like I talked about earlier, we have matching, stratification, and covariate adjustment with regression. Just like we had without propensity scores, now we're going to introduce propensity scores into it. So one way to do it is matching. So there's probably more than 3 methods for matching, but one is the nearest neighbor matching, which simply, I can't remember if the next slide has that here. Okay, nearest neighbor matching would be, if you had a small data set, you could do this yourself. You would take a case or someone who is treated, who has a propensity score of, say, 0.84, and you would look at the control person who had the propensity score closest to that. Even if it was 0.78, if that's the closest, that's fine. And you would do that until you matched every single person of the smallest group. If the treatment group was smaller than the control group, you would end up with extra controls. Just going to match 1-to-1 by the nearest propensity score from one person, and then to the nearest score in the person of the other group. Another one is caliper matching, in which case you set a limit to how far apart the scores can be before you consider it a match. I mean, if you were forced to take a match with a 0.72 and a 0.18, it doesn't seem like they have anywhere near the same score. So a caliper is often set, for example, 0.05, 0.02, some number that's fairly small, and you will not match someone who's outside that range. As you might expect, you would get fewer matches that way, but they'd be more accurate. And finally, there's something more complicated, which has to do with Mahalanobis distance, which I'll give you a quick example of, since it's not well understood in general. So you match subjects on that one score, right? The propensity score, instead of matching, as you would without propensity, to all these different covariates. Men have to match to men, and so on. Here we take the one score, the numeric score between 0 and 1, unless you happen to invert it, and you match them. There's matching software within 3 of the major programs. And if, I don't know, does anyone use Stata? Okay, and how about SAS? Okay, and then SPSS, okay. So in at least the later versions of, I think, of SPSS, I forget what version it started, but there is propensity score matching as well as case control matching under the data tab, and you probably have to learn how to do it. You can't do it out of the box. I think it'd be too hard. So if we match on propensity scores, we take a certain score that's maybe a certain range, and we get someone in who didn't get treated, we'll call that treatment A, and someone who got treated, call that B, and we have those 2 people match. They have very similar propensity scores. We can then compare the treatments. Well, we would look at eventually when we get to the outcome, we will use these matched pairs to see if there's a difference in outcome between each pair. In other words, if a given pair which has a similar propensity score, one of whom was treated, one of whom wasn't, if you then looked at outcome, and in each group, the treatment person did better, you would say the treatment was good, because comparing that person to someone very similar, the treatment always resulted in a better outcome. Are you familiar with using matched pairs for analysis at all? Okay, so if they're similar, we ought to see similar result, unless there's something about the treatment itself that makes a difference. And when you do this, though, you will exclude unmatched patients. As we saw earlier, at the end of those distributions, it's kind of hard to match people when there's only one group that has those scores. So in this example, again, if you did matching, instead of doing nearest neighbor matching, you did some caliper matching where you said the patient had to be within a certain range of another patient to be matched. Probably most of those people in the shaded areas would not be matched. You would lose them for the analysis. And this basically always happens when you do matching with propensity analysis. It's just one of those things. So there's a trade-off. Do you try to maximize exact matches so that you say these are really similar, but then you may even not be able to match some of your cases, so you're going to lose information. But if you try to maximize the number of cases, then you have an inexact matching, and that will maybe lead to inexact results. So you're always trying to decide which one is best. Okay, so sort of in another way of looking at nearest neighbor matching is select the first case. It's usually the case with the smallest group, whether it's treatment or not. It's the group that's smallest. Find the control or the other group with the closest propensity score. And again, I said this can lead to matching of very disparate scores pretty far apart. And caliper is define a range of difference and randomly select one control that matches on a propensity score of that participant. In a large data set, you'll probably find several in the other group with a similar score. And instead of doing it at random yourself, you can, if you use SAS, you can have a macro called greedy that is called greedy matching, and it takes care of that for you. Now, this is a little bit trickier, so I just wanted to give you a flavor of it, but it's another method to choose one control from multiple possible matches. And probably, I don't know if anyone in this room, maybe one person, maybe two, knows anything about what that equation says. So it basically tries to see how far apart the two, the case and the control is by something called Mahalanobis distance, which has to do with matrices and transposes and inversions, and that's goes too far for me, actually. So you do this, and whenever you find a case and a control or a treatment and a control that match, you take them out of the data set and keep going to the next person that you're going to match. And just as a two-dimensional example, if you had just two variables that you were plotting instead of from the propensity score, you can look at many variables or not. You notice that the T's are the treatment group and the C's are the control group, and the values plotted education in years versus outcome, and typically you wouldn't plot the outcome in propensity analysis, but for an example, if you wanted to match cases, you could see that those C's that are very far from everything else are just far apart from any T in terms of Euclidean distance, right? Just the distance. So if you match the T's to the C's, you can see that for any treatment person, you can find the closest C, take those out of the data set and so on, and you'll end up with what I think there's fewer T's and C's. All the T's will match. There'll be a couple of C's left over, and none of these C's on the right or left will be used, and that is what the Mahalanobis distance does, but in many dimensional space. So stratification. What can we do with a propensity score besides use the actual score and maybe match someone to it? Well, what we could do is, and this was done in one of the first articles by Rubin in I think 1984, he suggested breaking the scores into 5 quintiles, right? So the lowest 20% of propensity scores are quintile 1, the next 20% are quintile 2, and the 5th quintile is the highest 20%. And there will be, which makes sense, if let's say the A is actually, flipping around, A is actually the treatment group, there'll be more people in the highest quintile of people who actually got treated, because they're predicted to be treated, the highest quintile, say it might be 0.8 to 1, it might be some other range. And then on the far left, the lowest quintile are more people who got control, because that's the way the distribution goes. So you're looking at within each subclass, you can say, almost like we did with similar propensity scores similar to each other, within each quintile, probably the people in each quintile have similar propensity, although it could be kind of a range. And we can say, is there a difference of the outcome within each of the quintiles? And we can, it turns out that if the treatment effect is similar in each quintile, we found something. And we actually look at the overall average treatment effect within each quintile. That is, in quintile 5, does A do better than B with the outcome? In quintile 1, does A do better than B in the outcome? And has anyone heard of the Hosmer-Lemeshow test besides? So it's a test for goodness of fit, which can be done afterwards to see if you really have a good model for predicting something. Now, if you notice, it will use all the cases. Remember, we talked about extreme cases. There may not be anyone nearby with in the other group with a similar score. When you look at quintiles, you'll always have some overlap. So here's a way to, in a sense, use all the cases. Although, again, there's disagreement about whether all cases should be used or not. But if you do stratification and the trial size is small, some subclasses will contain probably only patients from one group. As opposed to what I just said, if it's a small study, I think this can happen easily. Some people have suggested deleting subclasses at the ends of distribution with 0 or even just a few members of one of the two groups, and just cutting them out, just as we would if we were doing matching and not matching people at the extremes. So we have different views about whether you can use all the data or not. And I think on balance, I think people are favoring not using all the data. And now there's a third method. We talked about matching, we talked about stratification, now about regression or adjusting in a regression model where the outcome is the outcome is a clinical outcome, and we're going to predict whether the treatment is related to that outcome. But instead of doing it with the complete imbalance, we're going to use the propensity score in some way, so we can have the propensity score as a covariate or a confounder adjustment, or we can throw in other confounders that we haven't looked at yet because they're related to the outcome, maybe not to the treatment group, but things that relate to the outcome. Or we can use strata of the propensity score rather than just the score itself. Instead of 0.86, we can say, does strata make a difference? And I've used 10 groups. Again, originally 5 groups were described in the literature. So there's different ways to throw that in as the balancing covariate when you're predicting the outcome by treatment received and then by some adjustment. So you can use logistic regression, and all these will include the treatment as the first predictor, but all of them are different. You can use then just the propensity score or the stratum. You can use matching and use conditional regression because you have matched pairs, although I've never seen that used in the literature. I've just seen simple regression even though you have matching because you have matched pairs. You could do conditional regression, which takes advantage of the matching. You can use regression adjusting for propensity score, but should you include, as some articles do, the covariates that you already have in the propensity score? That doesn't make sense to me if they're already part of the propensity score, but some articles have done initial regression with covariates, then they've predicted treatment group, then they get the propensity score, and then they do that same regression over again with propensity score. It doesn't make that much sense to me. And I've really never seen a clinical article published using the matching with that inverted weighting. And there are probably even more ways to do that. Now, I found an interesting article that said, what about imbalances that exist despite randomization in a randomized controlled trial? You could do something similar to the reverse propensity treatment score, and it was very complicated, but it looks at the probability of allocation based on allocations to that point in the study. For example, we know that, who's familiar with block randomization, where you have perhaps, let's say it's blocks of 4 and 6. So every 4 patients randomized to 2 treatments. If say the first person gets treatment A, the next 2 have to get treatment B to fill that block. Well, therefore, their allocation is not free. And these people have figured out a way to deal with that And they talk about an imbalance might occur because some of the randomization isn't, in a sense, free, something I hadn't heard that much about before. And if you're interested, again, I have about 7 articles at the end that I'm referencing for you to look up. Now let's go to the first study I talked about, and then to a study I did with some people, and then wrap up. So that article was from 2002, does early angiography in patients with ST segment depression or non-ST elevation MI do better? And it's observational, not randomized. So they had aggressive treatment within 6 hours or not. They had to be seen within 12 hours of their onset. And they looked at various outcomes, but the main one they were looking at was mortality. When they looked at the unadjusted, unadjusted groups, early angiography was only 2,000 out of about 20,000. And there was tremendous imbalance in all these predictors. I think they only had the ones that were significant, but that was too numerous to count. Differences in how they presented and what group they went in, which suggests a strong selection bias. If we look at the last line of this table, we'll see that mortality, again, as I showed in the first slide, was lower in the early angiography group, 4.9% versus 7.3 with the highly significant p-value. But we know that there's some selection bias, so how can we adjust for that? And of course, we could adjust for all those variables in multiple regression. We'd be doing that forever. Yes, I think this is probably done by chi-square testing, that outcome. Okay, but eventually we're going to do logistic regression, right? So this is actually multiple logistic regression. So each of these variables that was predictive with a odds ratio different from 1 are plotted here, and all those variables make sense in terms of cardiologists, that those things would be bad if you had them. And then early angiography, as you can see, is on the left of that 1.0 odds ratio. It's protective with an odds ratio of 0.76 and a significant confidence interval. And that's adjusted for those things. But we're wondering about selection bias, not, some of those might be involved in selection bias, but those are really implicated more in the outcome. So they did propensity score, and they looked at those variables that they initially threw in, did stepwise multivariate logistic regression, and get a propensity score for each person. And that's the probability that they would receive early angiography versus not. So then the people receiving early angiography are called cases, and they were matched to those not receiving it, called controls, using nearest available pair matching. So maybe not as accurate as some, but they actually did a 4-digit match. So they made the matching very accurate, actually. And they found 58% of the cases matched to control. So 1,405 patients with similar baseline characteristics. And when they did the analysis over again, now they say they did the original multivariate logistic regression. I'm not sure what original is. I couldn't find it in the article, but they are adjusting, whatever they're doing, they're adjusting for the matched pairs. And if you look here, we see that this is very important in articles about using propensity. You see what the balance is after propensity balancing. So look at the two groups. There's 1,405 in each group because they're matched 1-to-1. And if you look at the p-values, there's very few that are significant. Time to ECG. I'm not sure about non-Q wave MI. Difference in heparin, beta blocker, and calcium blocker, which may or may not affect things, but basically they're much more similar. Instead of all of them being less than 0.001, we see that they're fairly well balanced. And now if you look at the last line of this table, in the adjusted regression, we see that the death is the same in each group with a p-value of 0.87. And so there's no benefit to early angiography with an odds ratio of 0.89 with crossing the null hypothesis of 1. So here's an example of extreme selection bias that was addressed with propensity analysis. And finally, one that I worked on that was rejected from the journals for other reasons. But there were 528 patients from the VA who were selected because they either had esophageal cancer, they were the cases, it's a case control study, and 370 controls who were people with esophageal disease, something called Barrett's esophagus, which is thought to be pre-malignant. And they looked at exposure to Agent Orange based on probably an inaccurate measurement, which is those who were enrolled in an Agent Orange registry at the VA. They had to enroll, they had to be shown to be in a region that was used in Vietnam, but people could have not been exposed physically to it, or they could have been exposed but not enrolled in the registry. So the crude odds ratio, simply esophageal cancer case, predicting a case based on exposure, was 2.49, was significant. But when we looked at covariates that we had, we saw that age was very different, even though it's only a couple of years in esophageal cancer or not. And, exposure to Agent Orange or not. And BMI was different. Smoking was not different. So we used the propensity score, and we used it in 3 ways. First, we balanced on the propensity score. So we had esophageal cancer is predicted by Agent Orange exposure, yes, no, and propensity score as a continuous measure. The odds ratio decreased, but was still significant. Then we did it just using propensity quintile as a covariate rather than exact score, and it went down to 1.85, but still significant. And finally, when we did case control matching, because of that limited range of possible matches, we ended up with 85 versus 170 total out of the 500. And we see that the odds ratio is very similar to the quintile, but probably because of power, we didn't have a significant P. So one more bit of information. There was an article looking at comparing traditional regression to propensity analysis. So to have this work, they had to get articles that had both methods used, 43 studies, the kappa score of whether they agreed or not, the outcomes with propensity analysis and regression was fairly high. And when there were disagreements, I think there were 8, let's see, there were 43 studies and something at 70 some comparisons, and there were 8 studies, 8 outcomes that were in disagreement. And it said in every one of them, the regression was significant, but the propensity analysis wasn't, which is kind of bothersome. And that the odds ratio or hazard ratio on average was a little bit closer to the null with propensity analysis compared to regression. And these are studies that use both analyses. So limitations, in general, as we know, in observational studies, we really are limited in terms of saying cause and effect because we don't have complete balance in the groups, even with any adjustment we make. Propensity score methods can only adjust for observed covariates and not unobserved ones, something which randomization does a good job at balancing. It balances both. And it's better so to use propensity when we have larger samples. So we have more chances of doing matching, for example. We still have trouble in general making firm conclusions in no matter what model we use when we're not having a trial. And I keep saying that. When we take each person, we get their propensity score, again, the chances of being assigned to a treatment group compared to not. And we use that single covariate in various ways, matching, stratification, or regression. It's a methodology that can be used in addition to, but not as a complete substitute for traditional methods that I mentioned earlier, all the 3 methods. And the propensity score methods can suggest, because of looking at how the data are distributed with the propensity scores, when they're not enough overlap of that propensity score, we really know that we're comparing very different groups, and we may be limited in our conclusions about telling, about saying if group membership was related to outcome because of such different covariate scores or propensity scores. Again, if the groups are very different, how are we going to compare them with respect to an outcome? It just doesn't seem right. So I have about 7 references, the original ones. I don't think the original one by Rosenbaum and Rubin is there. I think 1984 might have been the second one. There's 3 there. There's the one about the, actually I did mention Sturmer, but basically it's an interesting article about the tails of the distribution where there's not much overlap. The reverse propensity score is mentioned at that article, and the systematic review comparing studies. And the last one was fairly complicated, but it showed really to me that each method is going to come up with a different result, and that you really have to have a lot of knowledge and experience with propensity analysis to decide what's the proper way to handle it. Because as you saw, even with my article, we had 3 different odds ratios, not that far apart, but which one is right, I don't know. You have to report all and let other people make their decisions. So I'm open for any questions. I think the context of that was it's more informative if you use that inverse probability treatment weighting, and that you, instead of comparing a tendency to be assigned to the treatment group, you're saying of those who had unexpected pairings, that is low propensity score, yet got the treatment, or high propensity score didn't, that's more informative in some people's minds than simply the tendency to be assigned to the treatment group. But it's addressing selection bias in a different way, which I thought was very different.
I'm sorry, could you repeat the question?
Oh, sorry. The question was, it looked like on one of my slides it stated that propensity analysis was more informative than something else, but I mentioned that that statement was only in reference to inverse probability treatment weighting, that's more informative to look at that number rather than propensity score. But I didn't mean to say that it's more informative than any other type of multiple regression, for example.
Thank you.
Yeah, the outcome is treatment group versus not, and predicting that. It's predicting who gets treatment by covariates. It doesn't matter if they get treated or not, but you're modeling the data, not looking at their exact assignment. Your score is your predicted probability of group membership, which you can ask for when you do logistic regression. So you get a score between 0 and 1, which is, again, the probability with that model that given person would have received the treatment, whether or not he actually did. But based on covariates that predict membership in that group, that one person, what is that likelihood that one person would be treated? And everyone gets a score from 0 to 1. Well, I don't think I used probabilities of group membership when I did logistic regression until I started doing propensity analysis, because you don't really need it necessarily. But you can, like, at least in SPSS, you ask for it as a additional, I think it saves it as another variable, and then you can use that in various ways, including constructing an ROC curve, which I don't know if all of you are familiar with an ROC curve, but if you did a model predicting an outcome with logistic regression, you can use the probability of membership in that group as the variable that you're seeing at which cutoff you get the best sensitivity and specificity for the outcome. I think it's getting, well, I don't know if it's getting to be more standard, but I think if you can do a multiple regression and realize if you're overdoing it with overfitting, then maybe try propensity analysis and see how similar you get of an outcome. But remember, if you do matching, you're going to end up using only part of your data. And if you don't use matching, you're going to include people at the ends of the each end of the distribution who are unlike people in the other group. And so each way, it's I don't know, you can get different results, and you have to then somehow interpret them and say, I believe these results because. You should have a fairly large data set. Yes, when you match, especially as you saw in my example, I ended up, not that 0.059 is a worthless p-value, but I didn't have a significant odds ratio with the matching because there weren't enough cases to match. Whereas in the example with the angiography for the heart, they had such a large data set that they could do the matching fairly well. And they didn't match everyone, but they had quite a big group. But again, someone might say, is the match, are the matched pairs representative of the whole study, or are they only a subgroup that had intermediate propensity scores, and therefore it's not a random subgroup? The question was, is matching ever done 1 to n rather than 1 to 1 in propensity analysis? And I haven't seen it used, possibly because usually in studies where it's done, that I've seen, the treatment and the control groups are nearly the same size. Where if you took it out of a cohort study, maybe you could have perhaps not that many exposures compared to the controls, and then you might do 1 to n. And I assume if you did that, you could probably still use some of the same methods, but I haven't seen it used. So for those of you who didn't hear the question, that was if you do more than 1-to-1 matching with more controls, you gain power and you don't throw out so much data. And is that useful? And the thought was, if compared to without propensity matching, in which case you might get a significant finding, and then when you do propensity matching and you lose a lot of data, then you don't get a significant finding. Can you gain significance by multiple matching? And I don't know, did you gain significance with multiple matching? Okay. Yeah. So the answer is we're not sure. Any questions from the other observers? From the rest of the audience? Anyone else have a question who's not in the room? Okay, thank you very much.